All right, for this video, we're going to look at a kind of an abstract style IB probabilities exercise, a problem really. So you're not given very much information at all here. You just have two events, A and B. We don't know much about them, whether they're independent or otherwise, but we do know, well, there is some sort of dependency, that the probability of A given that B hasn't happened is 0.6, and that the probability of A or B is 0.7. It's not a lot to go on, so first I'm going to start with a little bit of analysis. Some of the low-hanging fruit, as it were, just looking at information that I know, is if the probability of being A or B is 0.7, then the probability of not being A or B is 1 minus 0.7 or 0.3. When you carry that one step further, not only is that the probability of not A or B, you could phrase it as also being the probability of not A and simultaneously not B. In other words, probability of not A or B is synonymous with the probability of not A and not B in this case. If you look at a Venn diagram, that should make perfect sense. Just quickly showing, and draw some circles. So here in Venland, this would be A or B. Right, so basically, if it's not A and it's not B, then it has to be everything outside. So this is not A and simultaneously not B, everything outside, which, as you can see, is also, all the black stuff, is not A or B. So again, that's how this statement comes about. At some point, that's got to become sort of standard, self-evident kind of thing. Now, for the rest, I have to decide whether I'm going to use Venn or a tree diagram or a conditional probability table or some other tool to help me understand this. When I see conditional probabilities, sometimes I default to conditional probability tables because those are the ones that made most sense to me. However, I've been noticing more and more that a lot of IB problems favor the use of the tree diagram as an organizer. Moreover, when I see this, probability of A given that B hasn't happened is 0.6, then when I make my tree diagram, I'm going to choose B to be the first event because A seems to depend on the occurrence of B or not B. So here's how I'm going to set up my tree. We're going to start with the B's and then go with the A's. And before I actually put in any values right here, I wanted to codify each branch just as a reminder of how the tree works. Because we have distinct parts here, and sometimes they can be confused. Ooh, got ahead of myself there. All right, so here on this branch, B happened, and then once B has happened, either A can happen given that B's happened, or A could not happen given that B's happened. Now, if we multiply the probability of B times the probability of not A given that B, then we have the probability of not A and B. So the ands come as a result of the product of each line of, or each, pathway along the tree. The reason I did this is because it seemed like I was given so little information from the start that I had to at least know what I have to work with in terms of the big picture, so to speak. So what I see is this, not A and not B equaling 0.3. I see a not A and not B right here. So I'm going to highlight those because I happen to know that that value is going to be 0.3. I also know now the probability of A given that B hasn't happened is 0.6, which is this part of the branch. So I know these two values, and I could probably, because this is part of a branch, I can infer not A given that not B is going to be 0.4. So based on all the given information, this lower branch has all the stuff that I really want. And as a result, I'm just going to focus all my energies on that lower branch and maybe use it to figure out the probability of this unknown, not B. Because if I could figure out the probability of not B, then I could work it backwards and find the probability of B. So without any further ado, I just copied and pasted my tree diagram over here, and then I realized now that as I made the video, my Venn diagram got in the way, so we're going to get rid of that now and go back and show that branch. And I'm going to write a sequence or an equation that's absolutely true, and that is to say this, which is something I know, is equal to that times that, which is also something I know. So in other words, not B, probability times probability of not A given that not B is going to equal this and probability over here. So in other words, since this statement is true as a definition of conditional probabilities, we have now this unknown 0.3, or known 0.3, this unknown probability of not B, and then this, which is not explicitly given, but it is implied, since the probability of A given that not B is 0.6, the probability of not A given that not B is going to be 0.4. So we put that in, and that's an easy to solve equation. We just divide both sides by 0.4, and we get that the probability of not B is 3/4. And going back to our original tree, if this is a 3/4 chance to not happen, then we have a 1/4 chance of happening, and therefore probability B is 1/4. Now, looking at the mark scheme, this is essentially the first method in the mark scheme, which if you're watching on YouTube, you can't see. But if you're in my class, you saw there are 3 different approaches. This was actually akin to the first method, although it's a little bit clearer when you see it in a tree diagram. There are 2 other ways, one using Venn and one using another abstraction. They're totally viable, but not really easy to explain. This one is actually easy to follow and to generalize. You're not going to see this on your IB exam, but you might see something like this where they give you some information and it doesn't seem like it's enough. Sometimes just drawing out a tree or a conditional probability table will at least reveal some sort of branch that you can complete because you have enough given information. And again, just to summarize, you didn't work off the top branch because there was absolutely nothing given about the values on the top. So I had to work backwards from the bottom branch and then go over to probability of B from there. This makes it tough. So anyway, thanks for watching. Have a good day.